Alright, welcome to episode 2 of the Software Addiction Show. And today we're going to first read some news, and then we're going to have a segment where we go over how to make faster code in the browser. Let's get started. Alright, the biggest thing that happened is Firefox 44 came out. And let's look through and see if there are any relevant changes to us software developers. Let's see. One of the big changes for me is they made it so the keyboard, the on-screen keyboard, doesn't automatically pop up when you click on a text field, which it should pop up like that, which is what Chrome and IE does, but whatever. They turn that off intentionally for some reason. What else? The web developer tools, the inspector now has a lot better support for CSS keyframe animations. I haven't tried this out yet, but I'm gonna have to look into that later since I'm doing some keyframe animations. But that's great. What else? Oh, they added the Service Worker API, and what that's useful for is if you want to have your website work offline, so users can just type in the URL and it'll load from the browser even if they're not on the internet. Or if you've ever dealt with app cache, is what it's kind of replacing. There's no way to deal with really slow connections or intermittent connections, like if you get in a car and drive to a different location, or if you're on a train or you're walking somewhere and you switch connections. It really messes up a lot of websites. So this should solve that problem. And let's see. Unfortunately, it doesn't work in Internet Explorer 11 or Edge. But it does work in Chrome and Firefox and Opera, which is just Chrome. It doesn't work in the default Android browser, but it does work in Chrome on Android and Firefox on Android. And of course it doesn't work in Safari, because Safari's it's out of support, it seems. What else is new? Well, it's not listed here, but there's another API called the Push API, which is kind of related to service workers. And let's see. It works a little in Chrome. I guess that's why they're not advertising it that much, because it's not completely working. It doesn't work on any mobile. So it's just Firefox on the desktop and a little bit in Chrome. And what that is it lets you kind of run a background task without the web page actually being open. So it's like having a service. So you can do things like send users a message saying whatever, the website has some information for you. And I need to look into this because it's like really interesting. What happens when someone has a service, uses this in conjunction with a service worker to do something like mine bitcoins in your browser when tabs aren't open for users that don't know anything. Like, what's to stop it from doing that? I need to look into this more and see what else it can do, because that whole processing without having a tab open concept is really interesting to me. And let's see. I think that's it. I mean, there are a bunch of other features, but nothing else that we care about. Alright, what is next? Here we go. If you've ever used Emscripten, there's a similar project called, I think it's pronounced Chirp. It was called Duetto. Yes, we're running out of meaningful names. That's why we have to have nonsense like Chirp and Google and Yahoo and all that. But anyway, it's basically the same as Emscripten, which lets you compile C++ code into JavaScript, which is something we're going to be doing later today. The main difference between this and Emscripten is that it uses only C++, and it has a kind of more strict licensing setup where it includes some libraries in your generated JavaScript, and their libraries are GPL version 2. And for what that means is your generated libraries will have to also be GPL v2 licensed, because it's a copyleft license. If you don't know what that means, it means that your changes that you distribute, you have to make them available too. So if I were to take someone's project that's licensed under GPL v2 and make a change, I would have to provide that change to everybody under the same terms. But anyway, that's not a really downside for me, but I could see how some people would not like that if they wanted to do the free, if they wanted to do their own free project and not put it in the GPL, but put it under some other license like MIT or BSD. But I mean, if you're a company or whatever, they also have a commercial license and an enterprise. I'm sorry, an indie license and an enterprise license, which lets you get around those problems. And the other difference is it doesn't rely on the ASM.js under the hood to make the JavaScript even faster, which is just a bunch of hacks to make JavaScript think, or to make the JavaScript engine aware that certain variables can be treated as integers. Even though JavaScript doesn't support integer data types, it just supports float. So, well, that's one of the things it does. And it also allows for direct communication with the DOM, so you can like look at your web page and change stuff more easily. With Emscripten, it's not quite as simple. It's more segregated between that and the JavaScript. And it also, the memory model is just hooking into the JavaScript, whereas in Emscripten you have more of a big block of memory behind the scenes that it takes care of. And there are a few more differences, obviously, so look into that. I can't find any kind of release announcement, even though this was a few days ago, 1.2. But who knows? What else? There's a new web browser called Brave that was just put out in preview, a development version. It's basically Chrome, or I'm sorry, Chromium, the open source version of Chrome without the Google stuff. And it has a kind of a Safari looking theme. Like, it looks like it's on a Mac even if you're running it on Windows or whatever, which is kind of weird. But basically it's designed to block all ads and tracking and all that bad stuff and replace it with their own ad system, which is much safer. So you don't need to use uBlock or AdBlock Plus or anything like that. And obviously there's more to it, so go look into that. And the thing I wanted to highlight is a couple of hours ago, up until a couple of hours ago, if you wanted to try it out, you'd have to go to the GitHub page and find it. But now on their main website, they have a link directly to the download, so you can try it now. So I guess they're wanting more normal users to come download it and try it out. So go try it out. It's pretty cool. It runs basically the same as Chrome and has the same features as Chrome performance-wise. So it's not that significant to software development right now, but who knows. And that's it for the news. Alright, now to our primary segment. This is something I've been working on for the past few days. I've been always fascinated with making JavaScript faster in the browser because it's kind of the quote universal platform. It just works on anything. All you have to do is give a person a URL and then they can go there without installing any software or anything, and it'll just work on their garbage phone or their whatever, their Android, their iPhone, their Linux, their Windows, their BSD, Solaris, Haiku, it doesn't matter. The web browser is the platform. So I've been looking at all the various technologies that compile down to either JavaScript and run in the browser or something very similar. So down here there's a huge list of them. Emscripten, ASM.js, TypeScript, CoffeeScript, Hax, C#, Go, Dart, Knackle, Pinnacle, and some future ones which aren't even out yet that I'm really interested to try later, like WebAssembly, JavaScript with SIMD, where you get to access the SIMD directly, OpenCL and the WebCL. But I picked a few of those out of there, and I made basically a simple Fibonacci function, which I have a JavaScript, a couple different versions. There's an Emscripten C version, and then an Emscripten C again with fully optimized compiler settings, and its competitor Chirp C++, fully optimized, and then something a lot of people haven't been using, but it's called GLSL, which is part of WebGL. It's not really designed for doing computations like this. It's a graphical programming language. It looks kind of like C or C++, but it runs on the GPU. Like, it doesn't run on your CPU at all. So if you get your Fibonacci function and you can make it work on a GPU or spread out on a GPU which has hundreds of cores. I mean, your average GPU will have 30 to 100 and something processor cores inside of it. That could potentially be a huge performance gain. But obviously Fibonacci itself is hard to write to spread over multiple cores, so it would only use one or a couple if it's optimized. But anyway, let's look at the actual results. So here is the results for Firefox, and I'm going to show you other browsers too. So we have 3 different types of JavaScript. We have plain JavaScript, which took about 6 seconds, and then we have the same JavaScript with the directive use strict on there, which kind of limits what you can do to make the JavaScript a little bit tighter so it can be optimized easier. And that took less than 1%, or it was 0.5% faster, so it's not really meaningful. And then there's another hack that's been around for a while. It's kind of what ASM.js uses. You just do or0 on all your variables to let the browser know that you don't want that variable to be a float. You want it to be you're using it as an integer even though it's actually a float. So then that will kind of make it easier to optimize. But nowadays that's not really getting us any performance, because I mean it's less than a fraction of a percent faster in this browser. And then we have the real cool stuff where we have Fibonacci with C, and by default for some reason it doesn't use any optimization, so it was actually 61% slower. But then if you do use optimization with the 0 or the 03 flag, it was almost 50% faster, which is huge. So it went from 6 seconds to 3 seconds. And then very interestingly, the GLSL version was what is that, 1/10 of a second. And we'll look at the code because I'm not sure if that's actually correct. It might be optimizing the whole thing away. And finally there's the Chirp C++, which was only 25% faster, but that's really easy to write, and it's free basically. And let's see what other browsers got. Internet Explorer 11, basically the same for JavaScript, the use strict and bitwise manipulation didn't give us any real performance difference. The Emscripten was actually almost twice as slow, or over twice as slow, when not optimized. And then when it was optimized, it was still 1% slower, which is weird because usually Emscripten is faster. But I guess on Internet Explorer, it's not able to take advantage of the ASM.js that it's using under the hood, so it's not really going to be any difference. And then the GLSL, it's less than 1/10 of a second there, which it probably has the same problem as the other one, but it's still amazingly fast. And the Chirp, which was 10% faster. And let's see, Chrome. The same thing for the different types of JavaScript. No real performance change between usestrict and bitwise. Emscripten by default was way slower, and it was slightly slower for the fully optimized, which is weird. I think that's just because Chrome also doesn't understand ASM.js optimizations. The GLSL, way faster, less than 1/10 of a second, and the Chirp was actually slightly slower, which is weird. Anyway, let's look at the actual code that we have to do this. So we're running all the code in a JavaScript web worker so it doesn't block the UI, and the UI doesn't screw with the performance of the test. And this is all we're doing here. It's just Fibonacci. It's just calling itself recursively, and that little function everybody knows. Not really any difference. And then if you use the use strict version, it's the same thing. It just has use strict in here and up in the top here, just in case, TM. And then the bitwise version, it's the same thing, except we have the OR 0 over all the numbers. And I'm sure there's a way to optimize this further when I do more tests later. I'll be writing the ASM.js by hand, which will have similar optimizations. And then let's see, the Chirp, that's interesting. Let's see the code for that. It's just C++, and our Fibonacci function is the same as this. This other code here is just it's a wrapper class that exports this function through a little, JavaScript bridge. And the interesting thing about this is see, we have to make the bridge, and then we call the bridge.Fibonacci function. But the interesting thing is our generated code, it's tiny. It's only like 1 kilobyte of code. It's hard to read it now because it's minified, but it's absolutely tiny. Where if you look at the Emscripten version, the generated Emscripten code, it's huge. Let me see. Yeah, it's 480 kilobytes. It's half a megabyte. And if in the Chirp, it is 1 kilobyte, not even. Yeah, half a kilobyte. So that's pretty interesting. If you're concerned about ASM.js slowing down your Emscripten because it has to parse all that on start, and then there's also the download size consideration and all that, if that matters to you. And then let's look at the Emscripten. It's the same thing. You'll notice in the Emscripten, it's like a regular C program with a main. It even has stdio, and it's like if you write to stdio with printf, well, obviously you're running in a browser, so it makes it look like you're using printf, but it will actually do all the stuff behind the scenes to hook it up to the JavaScript console. Where in your chirp, I'm not doing it here, but it has its own way of talking to things, its own API, the client API, versus the Emscripten, which is more of a thing that wraps SDL and your standard calls to make it look like a regular C program, which has its ups and downs depending on which one you want. Oh, and then there's the WebGL version, which is much more complicated. See, when we run the JavaScript, we have to do all this extra stuff. With WebGL, we have to create a canvas, and then we have to, here we download the shader. If you've never used GLSL before, it's basically broken up into two different scripts: a vertex shader and a pixel shader, or a fragment shader, or whatever they want to call it. And each one will run on, it'll run the same function on each vertex or each pixel. So that's where you get the massive parallel part of it. That's how, if you write your code to be massively parallel and you have hundreds of cores, you can do some amazing stuff with this. Anyway, then we compile, and what it does is it actually downloads the source code to these shaders. They look like this. Like, here's the fragment shader, and here's the vertex shader. There's almost nothing in here because we're just getting the vertex and we don't use any of the data, but the fragment shader is where we do the actual work. It takes this, downloads this, and then here it the JavaScript sends the actual shader to the GPU. The GPU then compiles it and gets the result here. So it's not something that's pre-compiled, and that has overhead. So if you need to do a small calculation, you'll have to do that. If you have a small function to run, you're still going to have to do the overhead of sending it to the GPU and compiling it and checking all this stuff here. So that could eat up all your time. And then let's see, we get the two shaders, we combine them into a program, and then this is where it gets really complicated, where we have to create an input buffer and an output buffer. Basically, for each pixel in the input buffer, we run the function once. I'm sorry, the output buffer, we run the function. See, I'm confused, it's so complicated. We run it once, and then we can only access the input buffer for each pixel in the output buffer. So it's a lot more complicated. And I'm going to go into detail on how this actually works. This is just a quick overview. Obviously, it's hard. You can't just look at it and understand what it's doing. All that is used just to get the code, send it to the GPU, and then run it and get the result. And the actual thing that's running on the GPU is this fragment shader here. And let's see, our Fibonacci function is changed significantly. That's the actual function. One of the things that sucks about GLSL is that it looks like C at first glance, but it's very limited because it has to run on every browser. So they use an old version of GLSL, I think it's from 2008 or so, 1.0 maybe, and you only get regular integers, you don't get unsigned integers or long integers. You don't get bytes. You can't use recursion, so I had to change this function, and there's a lot of constraints on comparing values and if they're constant or not, so I have to do some weird stuff to make this even work. And this is also one of the reasons why it runs so quickly, I think, because if you look at the JavaScript Fibonacci, it uses recursion. And one of the things about recursion is it when you have a pure function like this, like a function that has no side effects, they could essentially replace Fibonacci 43 with the result in the compiler, and it would take 0 time to run because the result is always the same. If you call Fibonacci 43 a billion times, or if you call it whenever, it's always going to give you the same result. Whereas in here, if we do it without recursion, it's a lot more complicated, and it can't optimize it as easily. I'm sorry, it can optimize it more easily by default because compilers like to do that. Whereas the recursive version, it'll think you don't want it to be optimized by default, so it will be slower. Another thing I did a very bad job of explaining. But anyway, that's just a small example. Oh, and another thing that you can't do, you can't do any bit manipulation, so I had to make functions to do all that. That was a huge pain in the butt. There's no way to debug. Like you can't inside here you can't do anything like print to the console or set a breakpoint or anything. It's like a black box. You basically have to get your data, shove it into a texture as pixels, and then write it to pixels in your output texture and convert it back into bytes to read it. So you have to like take an integer, break it into 4 pieces, break those 32 bits into 4 8-bit chunks or 8-bit bytes, which are actually floats, and then convert it back and forth, which is a huge pain in the butt, especially when I was figuring out how to do this, because I would be converting it and it would break somewhere in there and I'd have no way to test it. But I finally got it to work in Eevee. Anyway, we'll look at this later in another episode, but that's a very cool thing. So in the future, I'm going to add some more tests. Fibonacci is very kind of non-parallel, but if I add some more tests that can be kind of broken down and be more parallel, we'll look and see how the different things, MScript and JavaScript and GLSL and Chirp, how those are giving us much different results, because then it can optimize our programs in different ways. And I'm also going to look at doing ASM.js by hand, TypeScript, CoffeeScript. Those I'm guessing they're probably going to be the same performance as JavaScript. And then there's this weird thing called Hacks, which I'd never gotten to work. Which I think you use Flash or ActionScript, and then it will compile that to whatever target you want, including JavaScript. And then there's C#, which should be interesting because C# has real integer support, so it would have to convert all that behind the scenes when doing JavaScript. And then the same thing with Go, which has real static typing integers. There's also Dart, native client, and Pinnacle. Dart has its own special VM, which is similar to JavaScript, or it can be compiled to JavaScript. Be interesting to see how that performs in different browsers. In my experience, Dart running as JavaScript runs great on Chrome because it's made by Google, and so is Dart, but then it doesn't run as good in Firefox or Internet Explorer. And if you never heard of Native Client or Pinnacle, they're basically a new VM it's kind of a competitor to Emscripten, where instead of running inside the JavaScript VM, it runs in its own separate VM, which means that basically your browser would need to have a separate VM to run it, which means Firefox will never run it and Internet Explorer will never run it. The interesting thing about Native Client is that it's operating system independent. So once you compile it down, it will run on your one program will run on Linux, Windows, whatever. And then the next step is Portable Native Client, or Pinnacle, which is operating system independent and CPU independent. So you could take your one exe and run that on whatever, your x86 machine or your ARM phone, and it would just be the one of them and it would work. It's kind of like .NET in that way, or Java, where there's kind of a bytecode. I think they actually use LLVM bytecode. Well, more on that later in some other episode. And in the future, people from Emscripten and Native Client are working together on a new project called WebAssembly, which is kind of like replacing both of those. Well, not really replacing them. It's kind of the next. Well, it replaces them, but it uses a lot of ASM.js and Emscripten stuff. And that should work in every browser with pretty much the same great performance that you get out of Emscripten in Firefox. And then there's some other stuff that's coming out, which is just OpenCL, which is you can do it in regular C and C++ programs, but not yet in JavaScript browsers, because they don't have the driver support. They're really the early version of GLSL, which it's built on top of. So what that means is this is an actual programming language designed for writing regular programs, not a graphical programming language, which GLSL is. So you don't have to do all those weird convert everything to texture and all that gibberish. It's more like a real language. And then the next step, which is really, 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 really exciting, is WebCL, which is where you just write JavaScript, or a JavaScript-like language or API, and then it'll convert it behind the scenes to run inside the GPU or the CPU or whatever. So you'll get a huge performance boost in most cases, and you won't really have to learn any of the complicated GPU programming stuff. But that's a way off. It's not even working in any of the browsers yet, but that's stuff to look forward to. I'm going to be adding more benchmarks. I need to figure out the performance issue, because obviously the GLSL should not be this fast. I think it's just being optimized away. But anyways, that's it. Go to our GitHub page, github.com/Software Addiction Show, where you can check out this stuff. If you find any bugs, and there probably are bugs in here, go in there and make a pull request, or just file a bug, or whatever. Or better yet, if you have a lot of experience with any of these other technologies, make another benchmark and help me fill this chart in here. So that's it. That's our main segment for today. Hope you guys enjoyed it. We're going to have a few more things before the end of the show. Alright, here's a couple quick things. Some cool tools I wanted to show you guys. One of them is, since we're doing benchmarking, the website jsperf.com. Probably already heard of it or seen it in some places, but this is still very interesting. Basically, you can make a JavaScript test, and then people can run it by viewing the page, and it will save the performance and show you what it's basically what I'm doing, but it's only the JavaScript part. I actually tried to use this for my benchmarks, but it's not quite compatible with doing things like mscripting and GLSL and all that. Like for instance, here's a test that shows jQuery's empty and HTML versus just calling inner HTML to clear an element. And this in this particular browser, Firefox 44, inner HTML is a lot faster. So this will track all those changes and show you what's faster. Pardon me. Alright, and the next website, another one you've probably already heard. We were looking at it earlier today when we were looking at the push API and the service worker APIs, is the Mozilla Developer Network, or developer.mozilla.org. Great resource for looking up new web APIs. Don't use that stupid W3 Schools website. It's often out of date or wrong or confusing. Use the MDN if you want to look up any kind of JavaScript or CSS or anything like that. Fantastic website. And actually, that is the end of the show. Thank you for viewing. If you guys have any feedback, if it's about any of the software, just go in here and file some bugs, or on our YouTube page. Actually, we don't have a YouTube page. I need to figure that. I need to set that up. Well, below this video, just post a comment or whatever. I'll have to put a Twitter page up there so you guys can tweet to me too. So alright, see you guys next time. Bye.